Welcome to The Explainer. Today we're diving into a story that completely shook the tech world. But honestly, it happened almost entirely in the shadows. We're talking about a stealth acquisition that went down in December of 2025. An AI hardware startup named Groq was quietly absorbed by a massive tech giant. But listen, this wasn't just your standard corporate merger. No, this was a highly targeted strike to eliminate a ghost that genuinely terrified the absolute biggest player in AI hardware.
Okay, let's dive right into this staggering $20 billion figure. That's exactly what Nvidia paid for Groq. And you know what the craziest part is? They didn't drop $20 billion just to acquire some fresh talent. They paid that astronomical amount to make a direct competitor completely disappear. Groq had actually built an AI chip that was running 20 times faster than Nvidia's absolute best hardware, all while using 10 times less power. I mean, Nvidia controls roughly 90% of the AI chip market right now. Governments are literally stockpiling their hardware. So when a behemoth like Nvidia structures a $20 billion deal specifically to dodge antitrust regulators and silently absorbs Groq's engineers, their patents, and their entire architecture just to fold it into their own next-gen hardware, well, that tells you exactly how dangerous this threat really was.
Section 1. The GPU memory bottleneck.
To really grasp why Groq was such a massive threat, we have to look at a fundamental physical flaw in the hardware. You see, GPUs were originally built for gaming graphics, not for running massive large language models. So when you force them to generate AI tokens, they have to undergo what I like to call the commute. Basically, every single time a GPU generates just one tiny piece of a word, it has to fetch the massive model's weights from the VRAM, drag all of that data over the compute cores, actually do the math, and then send the result all the way back. If your model is running at 40 tokens a second, that means the chip is making 40 agonizingly slow round-trip commutes to the memory every single second. The actual math being done, that part is basically instant. When you realize how this works, it's kind of wild. Your incredibly expensive state-of-the-art chip is quite literally just sitting there stuck in traffic most of the time. Moving on to Section 2, the radical LPU architecture. So Groq's billion-dollar solution to this problem was to introduce a completely new paradigm. They called it the LPU, or Language Processing Unit. And to make this reality, Groq had to do the unthinkable in modern computing. They had to fundamentally abandon traditional GPU memory entirely. By designing an architecture where the AI model never actually leaves the silicon die, their whole goal was to just completely eliminate that dreadful commute we were just talking about. The physical contrast between these two approaches is just stark. Modern Nvidia GPUs store massive amounts of data using traditional DRAM, which relies on just one tiny transistor and a microscopic capacitor. Now, because it's so small, you can cram tons of it onto a board. But it's got two massive flaws. First, those capacitors constantly leak electricity and have to be refreshed over and over. Second, because the memory bank is so massive, it can't physically fit inside the compute core. It sits outside, centimeters away. And when your chip is crunching billions of calculations a second, a few centimeters might as well be hundreds of miles. Groq bypassed this entirely by using embedded SRAM. SRAM doesn't use those leaky capacitors. It uses a locked, totally stable circuit built out of 6 transistors. And the kicker? It is baked directly into the silicon die itself. The memory and the math cores are literally millimeters apart. Because that SRAM is baked directly into the core, the data has absolutely zero commute. None. It's instantly available the exact millisecond the compute core asks for it. And that is exactly how the LPU is able to hit this mind-blowing raw speed of 80 terabytes per second. In terms of raw speed at inference, it absolutely obliterates traditional GPUs. No contest. Now you might be wondering, and it's a very pivotal question, if SRAM is a locked circuit that doesn't leak and it completely solves this memory commute to unlock 80 terabytes a second, why on earth doesn't an engineering powerhouse like Nvidia just use it? Well, this is where we transition from a miraculous piece of engineering into a really harsh physical reality.
Section 3. The massive memory catch.
The catch is that SRAM physically explodes in size on the silicon die. It pushes the absolute physical limits of semiconductor manufacturing. Because of that, when you compare capacities, it's almost comical. An Nvidia GPU, using that leaky, distant DRAM, can easily hold 80 gigabytes of memory. But a single Groq LPU, despite pushing the absolute boundaries of physics and engineering, can only hold 230 megabytes. We are talking about megabytes versus gigabytes here. To put that in perspective, you don't even get 200 kilobytes of this kind of ultra-fast memory on a standard GPU, so getting 230 megabytes is honestly a huge deal. But still, compared to 80 gigabytes, it's tiny. This means an LPU cannot train a model, it can only run it. And even then, it seems like a completely fatal flaw.
So how did they even manage to cram those 230 megabytes onto the die? They had to do something completely reckless. You see, Nvidia uses up a huge chunk of their silicon space by building complex, physical hardware to direct data traffic and schedule tasks. Groq realized that AI math, unlike unpredictable gaming graphics, is entirely predictable. So they just ripped out the physical hardware schedulers completely. Gone. They left massive amounts of empty space on the silicon and just filled it all with SRAM. But by deleting those physical traffic routers, Groq had to move all of that incredibly complex traffic control off the hardware and directly into their software.
Section 4. The real nightmare, networking.
Here's the plot twist. Because real AI models are hundreds of gigabytes and an LPU only holds a fraction of that, you have to stack hundreds of these tiny capacity chips together. Normally, chaining that many chips together causes catastrophic weighting bottlenecks. But Groq survived this memory deficit by creating a completely deterministic compiler. Before the code ever physically touches the silicon, Groq's software maps out the exact path of every single electron. It pre-calculates the entire journey of the data down to the exact nanosecond. The result is that the chips never actually have to stop and ask each other for data. They just execute their math blindly, and the software ensures the data arrives perfectly on time. This incredible software compiler forces 256 completely independent chips to act together flawlessly as one single synchronized brain.
And this brings us to a really core truth about this industry. Getting 10,000 GPUs to talk to each other without causing massive network bottlenecks is widely considered one of the hardest engineering problems on Earth. Nvidia didn't pay $20 billion for Groq's raw compute chips. I mean, Nvidia is already the undisputed king of raw compute. No, Nvidia bought Groq for their software. They bought them to rip out that deterministic networking technology, fold it right into their own next-generation GPUs, and permanently neutralize the only company that had successfully figured out how to beat them at a massive multi-chip scale.
So, let's leave things on this final, provocative thought. Nvidia absorbed their greatest threat, taking the definitive networking software completely off the board. If deterministic networking, and not just raw chip speed, is the true bottleneck to scaling artificial intelligence, and Nvidia now owns the key to that lock, who could possibly challenge their monopoly next? It's a question that is absolutely going to define the next decade of technology. Thank you so much for joining me for this explainer. I really hope this helped clear up the incredible story behind the $20 billion ghost. See you next time.